Good morning. It's a pleasure to me to introduce today Professor Denis Sabirov. He's the head of the Laboratory of Mathematical Chemistry in the Institute of Petrochemistry and Catalysis of the Russian Academy of Sciences. He's a physical theoretical chemist studying organic molecules like fullerenes and their compounds or derivatives. He's mainly interested in the theoretical predictions of the properties of these synthesized species. So, can I start?
Go on.
I'll try to make a presentation about the optimism and how it may be useful for astronomers. That is why I'm here in Instituto de Astrofísica de Canarias, and I'm really grateful to Dr. Aníbal García Hernández for his kind hospitality. And so let me start. Let me introduce my affiliation. It's Institute of Petrochemistry and Catalysis. It is organic chemistry institute, and we have several experimental laboratories there, and the only one theoretical laboratory called Laboratory of Mathematical Chemistry, where I'm head of this laboratory. And UFA, as you can see, situated on the borderline between the Europe and Asia, but in the Europe and its Canarias and Ural Mountains are two rather distant objects. But nevertheless, we are involved in a worldwide scientific community due to some international conferences like Cosmic Fullerenes. So, I just want to talk about what theoreticians see near his eyes, theoretical chemists see near his eyes when he treats his molecules, because we know that astronomers see the stars, comets and planets, and I'll try to talk in a simple language, and where it is possible I try to avoid some very sophisticated formula or overloaded numbers. So, mostly theoretical chemistry is associated with the quantum chemistry, and quantum chemistry is just an application of quantum mechanics to molecular systems, and chemistry in this way is knowing the energy as a function of nuclear coordinates. So if we deduce some, if we write some Schrödinger equation for a molecular system, it will be too complex to solve it. Therefore, there are many approximations to find out some approximated solution of such an equation. The first one is a Born-Oppenheimer approximation. It means within this approximation that you describe the motion of the nuclei and the electrons separately, and you can propose that nuclei are very massive particles, and you can treat it as static, and the motion in your molecular system will be attributed only to electrons. But even with this approximation, the Schrödinger equation is still very complex, and there are some other theoretical approaches to solve such electronic motion. There are semi-empirical methods, ab initio, perturbation theory, and maybe you meet before the density functional methods, because it's the most efficient methods today to reproduce the structures and molecular properties of very different compounds with a reliable time costs and needs of computational resources. So, if you divide your system onto the nuclei part and electronic part, you will come to the potential energy surface. It is the set of solutions of molecular Schrödinger equation with different fixed positions of nuclei. What does it mean? It looks like on this picture. It is a potential energy surface that corresponds to the ozone cyclization. It's a hypothetical reaction, and you may see that such a surface in a three-dimensional space has some minima and maxima, which are called stationary points, and the requirement for stationary points as the gradients of the energy over all the internal coordinates of the system should be 0, and the type of the stationary points is defined by a Hessian matrix. It consists only on the positive values if you are present in minimum that correspond to the stable molecules, and you have the only one negative value in the Hessian if you are stay in the transition state or saddle point. And here is a diagram of the cross-section of this potential energy surface. So if you have calculated the energy levels of transition states and products and reactants, you can now calculate the energy effects, heat effects, and activation energies of the forward and backward processes. So you can see from this plot that you don't need to have the potential energy surface in total. You just need some reaction path. Reaction path is a function of energy over some coordinates. It's a structural parameter that changes more significantly under the reaction. How does it work when you deal with the fullerenes? Here, my PhD work, just presentable. It's a reaction of addition of the ozone molecule to the C60 molecule. Many years ago, the experimentalists come to us with a question. Which bonds are more reactive in the C60 structure toward the ozone molecules? And we have scanned this reaction via the different reaction sites, 6-6 bonds and 5-6 bonds. And as you can see, when ozone and fullerene molecules are approaching, they go to the valley of the pre-reactionary complex. It is a minimum of the potential energy surface, which then converts into the final product, the fullerene trioxylanes. And we have chosen the 6-6 addition mode to the fullerene because it has low activation energy and process this molecule for further computations. So if you have activation energies and heat effects, you can calculate, for example, rate constants that via the Eyring equation, and to compare your calculated rate constant of such reaction with the experimental one. But let's go to the theoretical chemistry again. Of course, the most important thing here is not to calculate the energy of the molecule itself, but to calculate some useful properties. And when we talk about the molecules, we mean molecular properties. They are defined like a partial derivatives of the energy with respect of some parameters that could be electric field, external magnetic field, nuclear magnetic moment, changes in geometry. So, for example, electric dipole moment is the first derivative of energy with respect of the applied electric field. The polarizability is the second derivative with the external electric field. And so one of the important molecular properties for astronomers is a harmonic vibration of frequencies that are calculated as a second derivatives with respect to the change in geometry. So you obtain the fundamental frequencies that you can see in your infrared spectra of the compound of your interest. And IR intensities could be calculated as the mixed derivative toward the electric field and change in the geometry. So we have met with such a derivative. It's a matrix of Hessian. So when you attribute your stationary point on the potential energy surface to transition state or to a minima, as a bonus you will obtain immediately the IR lines in the IR spectrum of the molecule. Just a case from the fullerene chemistry. This spectrum was registered by my hands on very old spectrometer in our institution, and you can see the 4 fundamental harmonic frequencies, vibration frequencies of C60 fullerene. They can, of course, they can shift it slightly depending on the conditions whereby they register it, but nevertheless they coincide, for example, for laboratory conditions, astrophysical conditions in some molecular cloud, and of course you can use the density functional theory methods to simulate these lines. And as you can see, you can match the perfect correspondence if you use my preferable density functional method PBE triple zeta with experimental one. But you should know that B3 leap with the same basis set provides less reliable values, but nevertheless they are close to the experimental one, but they are less reliable. So, and here is the most important issue of computational chemistry, is just to choose an appropriate computational technique to reproduce the property of your interest. And for the fullerene science, I just should say some words how has it started. It started from the astrophysical topic, what's happened with the carbon-rich environments in carbon giants or red giant stars and in the surroundings of these astronomical objects. To simulate in stellar conditions, Grotto, Smalley and Curl have simulated in their mass spectrometers some laboratory approximations to such stellar environments, and they make laser ablation of graphite, and they were sure that they will obtain some polyion chains, but at high helium pressure in mass spectrometer they obtain the line corresponding to C60. Of course, such a long polyion chain couldn't exist, and they tried to understand what's the structure of the peak they obtained. And they come to conclusion that it has like a soccer ball molecule, but before 10 and 15 years before the experimental observation of C60, there are two works that should be remembered here because they're theoreticians like me. It's Eiji Osawa from Japan. He published in a Japanese language journal the paper that is called Super-Aromaticity Molecular Systems. You should trust me that it is translated from Japanese like that. And he make a picture of the molecule and propose that it should be super-aromatic. And some years, 3 years later, Dmitry Bochva and Elena Galpen published in the Bulletin of Russian Academy of Sciences the computational work where they used simple semi-empirical method to treat such molecules constructed from the carbon atoms and having a shape of dodecahedron and icosahedron. And they came to conclusion that this molecule should be unstable and this molecule would be very stable. But these molecules has no significant influence on the experimentalists at that time because it would be too fantastic structure and too enormous synthetic efforts to obtain such a structure in laboratory conditions. So these work were forgotten before the experimental observation of C60 under mass spectrometry experiments. So let's make a short chemical portrait of C60 and other fullerenes. Fullerene C60 has the atoms, carbon atoms, all equivalent in its structure, but at the same time it has two unequivalent bonds. 6-6 bonds are the common bonds of two hexagonal faces, and 5-6 bonds are on the connections of the pentagon and hexagon. Osawa wasn't right when he called this structure super-aromatic, because, and not Osawa and his but other scientists, because such 6-6 bonds behave like double bonds in the polyconjugated polyenes, like butadiene and its analogues, and 5-6 bonds behave like simple, ordinary carbon-carbon bonds. So most of the addition reactions to the fullerene molecule occur from these bonds. But there are some exceptions and some extraordinary reactants and photochemical transformations affords some 5-6 adducts. But the fullerene molecule is not an aromatic. It behaves like an unsaturated hydrocarbon, but without the hydrogen atoms. And it's rather reactive molecule, and it catches some chemical groups, organic or inorganic, to its surface. A little bit more complicated with the fullerene C70. It has lower symmetry, D5H symmetry, and there are 5 types of the bonds labeled by first letters of the Latin alphabet A, B, C, D, E, and in the backward order D, C, B, A. And so they have these vertices, atoms have different reactivity. So the chemistry of C70 fullerene is more sophisticated than the chemistry of its nearest kin. Why fullerenes are special molecules? The secret of the fullerenes is in the combination of non-trivial properties, such as rich spheroid three-dimensional system of pi electrons, inner cavity that can host the atoms from the outside, nanoscale size, and so on and so on. Many other compounds has the similar properties. Now, for example, the large polyconjugated systems are also porphyrines, inner cavity you can find in zeolites or cage silicates, and so on and so on. But the combination of such a list of properties you cannot find on any other class of compounds. As for comparison with the carbon allotropes, the fullerenes are the only molecular form of the carbon allotropes. So if you treat the molecule in contrast to graphite, diamond, nanodiamond, and nanotubes, you deal with the molecules with a finite empirical formula. It's for the theoreticians. What's the bonus for experimentalists? This is the only solvable form of carbon. It means you can dissolve C60 in the most of organic solvents, and then you can involve fullerenes to chemical transformation and obtain a variety of the fullerene different compounds, such as fullerene adducts with the simple addends, with multiple fullerene cages, or even the fullerenes. And that is why fullerenes attract with their structure. You can functionalize them with other chemical groups, and astrophysical interests were forgotten until the identification of fullerene molecules in space, which was performed in Kami group and performed in our colleague from Institute of Astrophysics of the Canarias, Dr. Garcia Hernandez, and they found that such molecules are very widespread in the universe. Why fullerenes exclusive compounds even in the universe? If you see the list of the interstellar molecules clearly detected at the moment, you will see that these are all very small molecules, and fullerenes looks like a giant among the other interstellar species. Let's talk about these species. As you can find from the previous chart, some of the contents correspond to different isomers which are abundant differently in astronomical objects. You can find that some of the isomer is major or more abundant, and some of the isomers are minor and less abundant. How to explain the differences in abundances of such isomers. In physical chemistry, you can, and in theoretical chemistry, you can again go back to the potential energy surface. If the energy of the isomer 2 is lower than the energy of the isomer 1, it should be more thermodynamically stable, and you should expect that it should be more abundant. But it would be too simple if you have come to such a conclusion only from the potential energy surface analysis, because the nature are more diversified than we expect. And in some cases, this energetic approach, this minimum energy principle, works, but in some cases doesn't. And we were interested why and how we can correct theoretical situation to predict the situations when the minimum energy principle doesn't work. And we try to use for this purpose a molecular property, dipole polarizability. It's a molecular property that defines the behavior of a molecule in the external electric field. And the polarizability tensor is a linear coefficient between the vector of the induced dipole moment and the strength of the field. And in experimental studies, you can measure mean polarizability and anisotropy of polarizability. And for computational studies, we use finite field approach to obtain the components of polarizability tensors. Then you can diagonalize this tensor and to calculate mean polarizability and its anisotropy. And we will not stop on the computational protocols, but we talk about the universal nature of polarizability. As all the molecules can be approximated as the electric fields that influence the molecule of your interest, which is placed in the box with the other molecules. This influence can be approximated like electric fields. That is why polarizability relates to many physico-chemical properties such as dielectric permittivity, refractivity, intermolecular interactions, and so on and so on. As for important for astrochemistry and astrophysics, polarizability relates to the interaction of the organic compounds with elementary particles such as positrons. Here again, the positron is approximated as an external electric field that influences the molecule, and its response linearly depends on the polarizability, dipole moment, and some other properties, but the correlation exists. And of course, there are the similar principle, like in the case of the energy, called minimum polarizability principle. It claims that the most stable isomer should have the lowest mean polarizability. But it is a correlation, and minimum polarizability could be violated. Let's check. Oh, and a few words why we pay attention to polarizability. A few years ago, we have obtained such correlations between the anisotropy of polarizability and the photovoltaic performances of the fullerene-containing organic solar cells. It means that polarizability may be responsible to the interaction of the composite materials containing fullerene and polymer toward the sunlight. So why don't we use polarizability for the interstellar chemistry? So it's just a chart, and we avoid the numbers. I just say that in most cases, the most stable isomer, as predict minimum polarizability principle, corresponds to the lowest mean polarizability, but in some cases isn't. And here are two examples. The first one is a concordance with the energy estimates, polarizability estimates, calculated values, and the measured abundance. You will see that the lower energy, the lower polarizability, the higher abundance. But in some cases, the discordance between the energy estimates and polarizability. And here, polarizability correlates with abundance. It is a case of methyl cyanoacetylene and its cyanoalene analog. Of course, situation is even more complicated. What we do in a theoretical chemistry laboratory? Abundance depends on two factors. favorability of formation, and you can estimate it by the energy estimates, and propensity of the molecule that has been formed for further transformations, and you can approximate it with polarizability. But observed abundance is rather different from that one, because in addition to formation and the reactivity of the molecules, there are also observational factors such as uncounted physical chemistry, features of astronomical object, and experimental techniques. For example, unaccounted physical chemistry means that molecules in interstellar medium can be absorbed on the ice particles or on silicate grains, and they may be invisible for your observational techniques. But quantum chemistry can help with the estimation of energy, reactivity, and maybe with such complex physico-chemical phenomena. In the case of the Fullerene compounds, polarizability may be in the agreement with the energy estimates and maybe with a disagreement. These slides show the agreement case. So for the 6,6 adducts, which are more stable, we have lower mean polarizability values. The same from the adducts of C70 fullerene, as you can see from this chart with the oxygen-containing derivatives. The more interesting of the laboratory chemistry of fullerenes is the disagreement between polarizability, energy estimates, and what do you observe in the laboratory experiment. For example, these two structures of C60 of C70 could be obtained under the ozonation of the solutions of the C70 fullerene. And according to the calculations, the most stable isomer is AB, and its formation has low activation barrier. But in experiment, this isomer leaves shortly, and the more abundant isomer is a C70O3. If we calculate the polarizability of these two regioisomers of the C70 triexcellence, we will obtain the following relation, that this is the least polarizable isomers. So polarizability reflects the further chemical fate of the compounds obtained. And between these two isomers, the transformation of the most stable isomer requires low activation barrier, so it vanishes in your experimental system. But you can estimate these activation barriers. But if we deal with the complex chemistry, sometimes we do not know in what compounds our compound of interest do transfer. So it's the similar case, but it's more strict, because you can even observe AB isomer in the experiments, and it is disfavored in terms of polarizability. And CC isomers are favored in terms of polarizability, and energy estimates doesn't work here. As for more complex compound of C60, such trimeric molecules, you can find that the yield of such multi-cage compounds goes down with the increasing polarizability of the system. Another chart is devoted to the polycyclic aromatic hydrocarbons. We have described in the terms of minimum energy principle and minimum polarizability principle the sets of the isomeric series of anthracene, tethracene, and pentacene, where it is molecule somewhere between these. Oh, here it is. And we have found that the compounds with the lowest energy are flat aromatics, and the compounds with the low polarizability are non-planar aromatic. Like helicene molecules, it's a helical-shaped benzenoids that in fact are hero, and this was only a proposition made by us last year. And this year we have found the work and myth with the authors in Russia. The work published in Nature Communications of the joint group of Ralph Kaiser, its experimentalist, and Alexander Mebel, is a theoretician, which were devoted to the simulation of circumstellar envelopes conditions in the laboratories. And they have found that under such conditions, they observe experimentally the formation of 4 helicene instead of flat hydrocarbons. And they proposed that in addition to the 4 helicene, there were formed 5 and 6, and they show it by computations. So I think that our prediction have the first confirmations. We go further, and we have calculated some polycyclic aromatic hydrocarbons in the pairs 2D and not 2D. And we have obtained almost the same regularities with some rare exceptions. Of course, it is a correlation. Favored in terms of polarizability are the non-planar aromatic hydrocarbons, but favored in terms of the energy are flat aromatics. And we stress this moment because pHs are the most known candidates for observation in stellar conditions, and the researchers, astrophysicists, are focused mainly on the flat molecules. And we recommend also include to the focus of your interest the non-flat aromatics. And polarizability, of course, may be applied to the sets of the related compounds such as polyines, cyanopolyines, and decyanopolyines. And we can see that the yields of such polyiene molecules decreases, and is in experiments energy rushes to some constant value, and only polarizability is inversely correlated with the observed yields of the cyanopolyienic molecules. As for C60 chemistry, it is interesting that C60 could be hydrogenased because it is unsaturated compound, and the hydrogen is one of the most abundant elements presented in the universe. And there are a lot of fullerene hydrates, but these are mostly unstable compounds. How to rationalize their instability? You can do it in the terms of energy, and once again you will obtain no interesting values because these structures are favored in terms of energy, but the first compounds of this set, the first homologues of this class are disfavored in terms of polarizability, and maybe this is the reason why the fullerene are not hydrogenated in the interstellar conditions. But situation may be improved if we deal with such adducts of polyene, cyanopolyienic chains attached to the fullerene core. Let's talk about the exclusive C60 molecule. I skip this slide. How to model in the theoretical computations the formation of fullerenes. You may, Early and Marakuma were succeed in molecular dynamic simulations in which the started compounds were C2 molecules, and they heated their system, and they obtained the chains, the cycles, the balls, and the cage structures. The problem is the structure they were obtained are the large fullerenes, about 300 atoms per molecule, but in the experimental values, experimental observations, you see only C60 molecules. Osawa was criticizing such approach, and he proposed that such giant fullerenes may be deflated, forming such a double shell ball, double onion, and then such a structure can eject C60 from its interiors. We try to model such a compression in the symmetric directions in the places where heptagons are in the molecule of C240. And we were unfortunately found that such a process is energetically very unfavorable, but you can find the C60 structure inside such aggregates. But we stopped such studies because of drastical energetic disfavorability. And we decided to close our eyes on the energy values and polarizability values and to treat our fullerene molecules in terms of information theoretic approach. In such approach, you can divide your molecules into the unequivalent atoms and to calculate the fractions of each group of unequivalents and to calculate such a value that is called information entropy. And this value inversely correlated with the symmetry and linearly correlated with thermodynamic entropy. And we have calculated such a parameter for more than 2,000 structures, fullerene structures. And we found that most of the values corresponding to the fullerenes are crowded on the top of this dependence. And the only few points goes inside of the interval between the values of the two most abundant fullerenes detected in space, C60 and C70. And we try to treat this interval more precisely, and we found that it is about 1%. And if we'll take into account the Gentile symmetry reduction effect, this amount would be much lower. Of course, this sortation is not so good as it seems, because some experimentally observed fullerenes are not fitted into this interval, but nevertheless, we think that it could be improved. And this slide shows that C60 has very survivable fullerene cage. Even if you put inside some reactive interiors, like such a water endofullerene that has been synthesized by the Japanese organic group, if you flat, of course, if you depress such an endofullerene, of course, in the computations, and then relaxed, you will obtain exactly the structure of the C60. And I'll try to make a video, but I think it don't work, but nevertheless. I'm going to the conclusions and challenges of fullerene chemistry. Why fullerenes are also interesting. In some very recent works, 17, 18, 19 year, some Matilis group has obtained experimental values of the catalytic activity of such a set of fullerene catalysts. And fullerene containing compounds can catalyze such condensation reactions, and even the presence of the fullerene compounds in such a system may reduce the byproduct of decarboxylation that doesn't lead to the growing up of the molecular size. Why it is important? Also, one of the very recent work is devoted to the fullerene radiolysis in astrophysical ice analogues containing ammonia and methanol. The collaborators has obtained a set of the organic molecules which are in nature has carbonyl groups and amino groups, and these are amino alcohols, amino aldehydes, and maybe fullerenes can catalyze the formation of such complex organic molecules, and we can even speculate that fullerenes may be relevant to the problem of the formation of the life building blocks. And before the conclusions, I just stress how the experimental and theoretical science could be interacted, and it's the free modes. When you have complete experimental values, you can use the theoretical science to rationalize your obtained experimental values. If you have incomplete experiment, you can complement your experimental data with the calculations, and of course you can hypothesize some structures that are not exist nowadays, but you can predict that they can exist in synthesis or in laboratory conditions or environmental conditions. And as a conclusions, they will be showed that the nature is very complex and we should use jointly energetic parameters, molecular properties, structural descriptors to obtain the whole picture of the chemical processes that take part in natural terrestrial or extraterrestrial environments. And as for the logo of our scientific group, we claim that polarizability closely relates to chemical processes that involve fullerenes, their derivatives, and pHs. Thank you for your attention. Okay.
Thank you for your nice talk, and also very interesting. Yes, I have a little hurry, and one question about electric dipole moment, the hydrogen atom fullerenes. Is it with one or two hydrogen? And do you know the electric dipole moment? What is the more stable of the hydrogen atom fullerenes with the C60? The fully hydrogenated or one or two or three hydrogen?
Okay, I'll try to find some slides.
Do you know the electric dipole moment in the bar?
Yes, we have calculated electric dipole moments because we obtained it in our computations, but we haven't analyzed them. Some of theoretical works analyzing periodicals, I saw such works, but it's difficult to talk about that. But nevertheless, the presence, yes, it's only polarizability computations. And I think that a dipole moment from, C60 is a non-polar structure, then when you add a hydrogen to your C60 core, you will increase your dipole moment even if it's a hydrogen, because I mean even because fullerene hydrides are often treat like analogs of C60 fluorides, and fluorides of C60 are very polar structures. And for such a structure like C60 F18, it has the dipole moment about 10 dBs.
10 dBs,
C60 with the fluorine, but I propose that this structure should be also very polar. Not as a fluoride, but nevertheless, it should be polar, because you will see, if the molecule is divided onto two parts, carbon-rich and hydrogen-compensated. Yes. If you're interested in the dipole moments, I can provide you computational value, because we have already done such calculations, but we focused deeply on polarizability and doesn't involve it into our considerations. But if you come to other fullerene structures, such as highly symmetric C60H36, it has a tetrahedral symmetry. Yes, its stick model is under the chart. Yes, these structures, the structures with a lot of hydrogen are more stable than the low hydrogen analogs. The presence of hydrogen stabilizes, as we found, because we have met some other estimates which have been obtained with other theoretical approximations. But this structure shouldn't be polar because of its high symmetry, because your bond dipole moments of the bonds compensate each other. Okay, of course, yes. And I just remembered the additional about the C60H18, because such structures are aromatic, are locally aromatic. Because as you can see, the hexagon surrounded by hydrogen atoms is flattened, and the bond length, we have analyzed this feature, are equalized in the distance, and it is a identifier for local aromaticity, and aromaticity, as we know, stabilizes such molecular structures.
Okay, I have one curiosity. What do you think about photo switching as a possible mechanism to give an extra stability to fullerenes or their derivatives? I mean, the fact that if one of these fullerene-based molecules absorbs a photon, could adopt another structure.
Well, about the interaction of fullerenes with some electronically excited states. You mean that one, yeah?
I say that because this phenomenon, the photo switching, has been observed in the interstellar medium for a much smaller molecule.
Well, we haven't analyzed it deeply on the fullerenes, but we have done some calculations for fullerene dimeric compounds with the switching, which have which can exist in two states, with a lower polarizability and with a higher polarizability. But we have just compared the molecular parameters of such structures, but we haven't calculated the interaction of C60 with such disturbing influence, because it requires very complicated time-dependent computational techniques, and we just on a way to make some these resourceful computations.
Okay, thank you.
Okay. So should we? Okay.